Alright, in this short video, we're going to go through some concepts that deal with solving linear equations and inequalities. Alright, so first things first. A linear equation in one variable is any equation that can be written in the form mx plus b equals c, where x is a variable and m, b, and c are constants, and m does not equal to zero. M is not equal to 0. So what this is telling you is that if you have a linear equation, it might not look like that, right? It might not be written in that form initially, but you can get it into that form, right? And if you notice, that looks very similar to y equals mx plus b, which was the slope-intercept equation of a line. The only difference here is that m, b, and c are all constants. The only variable in this case is x, right? Whereas when you have y equals mx plus b, slope-intercept form of a line, x and y are both variables. So that has two variables, whereas this only has the one variable. Okay? And of course, to form an inequality, all you have to do is replace that equal sign with one of the four inequality symbols, which would be greater than or equal to, less than, or less than or equal to. And, I mean, very simply, you've then formed a linear inequality rather than a linear equation. Okay? Now, generally speaking, and this is probably, 99.9% of what you've dealt with in the past, most linear equations are going to have one solution, a single unique solution. However, there are instances where linear equations can either have no solutions, right, zero solutions, or they also can have an infinite number of solutions. All right, and again, these don't occur frequently. However, they can show up. So first, real quick, an example of something that would have no solutions would be something like x equals x plus 1. And I mean, just logically speaking, you look at that and you say, well, clearly that can't happen, right? Because some number cannot be equal to itself plus 1, right? So this would be an example of one that would have no solutions. And I mean, you can even try to solve this. I mean, you would just follow your basic equation solving steps, which we'll get into in the example video. But like, the steps would pretty much tell you get all the variables on one side, right? Because right now you got variables on two sides. So if I want to get all the variables on one side, I would subtract x from both sides. But when I do this, what ends up happening? Over here I have 0, and over here the x's cancel, and I have 1. So I end up with that false statement there. So that would tell you that this equation here, x equals x plus 1, would have no solutions. It would be called a contradiction. Which makes sense because 0 equals 1 is a contradiction, right? And then on the other side of the coin, right, you have things that have an infinite number of solutions. I mean, something like right? 2 times the quantity x plus 2 equals x plus 5 plus x minus 1. I mean, I tried to make this a little bit more complicated, but it's still, I mean, it's a very simple equation still. And again, you can try to solve this using your equation solving steps, and our equation solving steps would tell us, well, first we want to just distribute and combine like terms on each side if possible, right? So on the left side we could distribute, we'd have 2x plus 4, and on the right side we can combine two x's, get 2x, and combine the 5 and the negative 1 and get 4. And already at this point you can see that, well, 2x plus 4 equals 2x plus 4. That's clearly a true statement, right? But again, you can continue with your equation solving steps. All right, get all the variables to one side. Subtract 2x. Subtract 2x. But now what happens here is on both sides, the 2x's and the negative 2x's are going to cancel, and you're just going to end up with 4 equals 4. So this equation here that we started with would have an infinite number of solutions, and this would be known as an identity, right? So if it has an infinite number of solutions, it would be called an identity. If it has no solution, it would be called a contradiction, right? And again, those are, the exceptions to the general rule of having one solution. Usually with linear equations, you have one solution. Okay. Now, how can you solve linear equations? Symbolically, which means, do them by hand. Very simply, right? You generally isolate the variable. Okay. Now, symbolically is the way that you're used to solving equations probably, but we can also solve them graphically or numerically. Right? Graphically obviously means by using a graph, and numerically would mean by using a table of values. Right? So, how do you solve them symbolically again? You isolate the variable. And how do you isolate the variable? In general, you're going to use what are known as inverse operations. Right? So what are inverse operations? They're operations that undo each other. Right? So, like adding and subtracting, those would be inverse operations. Multiplication and division, those would be inverse operations. Okay, so if I want to undo adding 5, I would subtract 5. If I want to undo multiplying by -3, I would divide by -3, so on and so forth. Right? So if I have addition, I do subtraction. If I have multiplication, I do division. And eventually, when we get into more complicated kinds of equations, you'll see if you're squaring, well, how do you undo squaring? You can take the square root of both sides. If you're cubing, you can undo that by taking the cube root of both sides, so on and so forth. But at this point, we're mainly dealing with addition and subtraction and multiplication and division being examples of inverse operations, right? They undo each other. And to solve numerically and graphically, what you'll see eventually is we'll create graphs and tables using our graphing calculator. So there really won't be a lot of written work to be done. It'll just be mainly done by the calculator for us, which is, nice. So here's our first simple example here. Solve 5 minus 1/3 x equals x minus 3 symbolically, numerically, and graphically. Well, solve symbolically again is the way that you're used to, right? So you generally had a process for solving symbolically. You would distribute, combine like terms, get all the variables to one side, get all the constants to the other side, and then multiply or divide at the end, all right? And it's the same concept here. Now, you might make the argument, well, I want to get rid of that 1/3 here first, and I can multiply by the LCD to do that, but we'll hold off on that at this point, and we'll just do this in a straightforward manner. So how would I do this? All right. I would get all the variables to one side first, right? So I have a negative 1/3 x over here and an x over here, so I'd probably add 1/3 x to both sides. So it cancels out here, right? Because I had subtraction, so I undid that by doing addition. Now on the left I have 5, and on the right I have 1x and another 1/3 x, so I really have 4/3 x. And then a -3. So I got all the variables on the right. Now I would move all the constants, right, or the numbers to the left. So I got to get rid of that -3 by adding. So now this is 8 on the left and 4/3 x on the right. And now how could I get rid of this 4/3? Well, you might say, all right, well, I'm multiplying by 4/3, so to get rid of that, I would divide by 4/3, right? But if you recall from elementary school, dividing by a fraction is really the same as multiplying by its reciprocal. So to get rid of that 4/3, probably the nicer thing to do is to say I'm multiplying both sides by the reciprocal, which would be 3/4. So now the 4/3 and the 3/4 on the right cancel, and I just have x. And I would have 3/4 times 8, which is going to be 6. Right? So my solution would be x equals 6. And of course I could check that in the original equation and make sure that it would work. And then I would end up with 6 equals 6. I'm sorry, yeah, 3 equals 3 on both sides if I did a check. Alright. Now suppose that instead of being an equation here, this was actually an inequality. Oops, sorry. If that equals sign was actually less than, how would I solve this? Well, I could solve it the same way, but what I'm going to do here actually is something slightly different. When we solve the equation, we move the variables to the right side. What if I move the variables to the left side? So if I got rid of this x, I would subtract x on both sides. And I would end up with 5 minus 4/3 x is less than negative 3. And then I would get rid of the 5 now, because it's on the same side with the variable, by subtracting. So I would end up with negative 4/3 x is less than negative 8. And similarly, I would get rid of that negative 4/3 by multiplying by the reciprocal of negative 4/3, which would be negative 3/4. So I multiply by negative 3/4 on both sides. And now this was the one exception, right? The one difference between solving equations and inequalities. When I solve an inequality, right, and I multiply or divide by a negative, what must I do? I must reverse this inequality sign. So this less than is going to now become greater than. The negative 3/4 and the negative 4/3 cancel, and then negative 8 times negative 3/4 would actually be a positive 6. So I would end up with x is greater than 6 in this instance. All right? And again, I have that boxed there as an important thing to remember. If when solving an inequality you multiply or divide by a negative number, the sign must be reversed. Right? Now the solution to that inequality that we had was x is greater than 6. Right? Now the solutions to inequalities are not just single numbers, as they usually are with equations. They're actually infinite sets. Okay? And how do we express infinite sets? Well, a couple different ways. We can express them in interval notation as inequalities, as we did there, or on number lines. Okay? So the inequality x is greater than 6 could also be expressed on a number line as such, right? I would have a 6 here, and the 6 is not included, so to show that, what I would do is I would use an open circle, and then I want to shade everything that is greater than that number, and on a number line, greater than means to the right. Okay, so I'm shading everything to the right of 6. So that would be the number line representation of that set. And I could also express that set in set builder, in interval notation. As parenthesis 6, comma, infinity. And usually once you get into interval notation, instead of using open and closed circles on number lines, you'll often see the open circle replaced with the parenthesis, right? But I would accept either one, right? Whether you use an open circle or a parenthesis, fine, right? But usually once you have interval notation, you usually just switch to the parenthesis and the bracket, as we'll see, okay? Now, set builder notation is something that you might see in our textbook. And I mean, it's very similar to the interval notation. What they'll usually write is, if that solution was x is greater than 6, they would just write it like this. They'd write a little set brace here. They'd write an x and then a vertical line. And then they'd write the inequality after that and then close the set braces. So really, it's just a matter of leaving your inequality, but just writing it inside these braces and then preceding it with that x and the vertical line. Right? I mean, the way that would be stated, if you saw this, what would you say? You would say the set of all x such that x is greater than 6.